Okay, this is a video lecture for Math 181. This video lecture is for Thursday, April 16th, and the topic today is the definite integral. Now, these video lectures have become quite large files, and so I'm going to start something new today where I basically break these up into a couple parts. So this is part one of our video lecture, and then I'll also do a part two. I'm also going to try to keep these video lectures a little shorter in terms of total time duration. Let's remind ourselves from last class. We're trying to find the area under a curve, okay? And the way we do that is we divide the area under that curve into a series of rectangles. We add up the areas of each rectangle, and we came up with this formula. The area equals the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x. So what we did is we divided the area under the curve into a series of rectangles. We add up the area of the rectangles, and this approximates the area under the curve. However, in the limit that the number of rectangles goes to infinity, this approximation becomes exactly the area under the curve. Let's remind ourselves here, f of x sub I is the height of our rectangle, and delta x is the width. So we're summing up all these rectangles, the areas of all these rectangles, in the limit as n goes to infinity. The new twist today is that it turns out this is actually the definite integral. So if you have some region, if you have some interval a to b, then the definite integral on that interval is represented by this sign. So the way we write that is we use what's called an integration sign. This is an integral, and the way we write this is the definite integral from a to b of f of x dx for some function f of x dx. It turns out this definite integral is defined as exactly this, as the limit as n approaches infinity of the sum I equals 1 to n of f of x sub I times delta x. Okay? So the definite integral is defined as the limit of the sum of all the rectangles. And let's remind ourselves here, delta x is the width of a rectangle, and it's equal to b minus a over n, where n is the number of rectangles. And our x sub I are the different points at which we sample the rectangle height, or the different points at which the rectangles are sampled. X sub I equals a plus I times delta x. So these are all our various x sub I, and this is the definition of a definite integral. This is referred to as an integral sign. And the other piece here to mention to you guys, some terminology, is this particular sum. This sum is called a Riemann sum. The term for that is a Riemann sum. We're going to do one example problem today. But before we do that example problem, I also need to give you guys a couple formulas that are helpful. These are helpful formulas. It turns out the sum of I equals 1 to n of I is equal to n times n plus 1 over 2. So if you're summing up a bunch of i's, this is what you get. And by the way, we're not going to prove this. This is you could prove this using sequences in series, but we're just going to take these as given. The sum of I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 divided by 6. Okay, these again, you don't need to know how to get these, and I'll give these to you guys. You don't need to memorize them, but we may need to use them later. And then finally, the sum of I equals 1 to n of I cubed is equal to n times n plus 1 over 2 squared. All of that squared. And these will be helpful. So what we're going to do now in our example problem is we're going to take a function and we're going to approximate the area under the curve by taking the Riemann sum of a fixed number of 4 rectangles. And that's only approximately valid. And then what we're going to do is we're actually going to take the limit as n goes to infinity of that sum to get exactly the area under the curve. But this is the basic theory. We already knew this. This is now the definition of a definite integral from a to b of f of x dx is equal to the limit as n approaches infinity of the Riemann sum of all the rectangles you're using to approximate that curve. Okay, let's do an example problem. And the example problem is this. Suppose we have, here's an example problem. Suppose we have some function f of x, and it's equal to x squared minus 2x. Okay, and in part A, what we want to do is we want to find the area under the curve. So we want to evaluate the Riemann sum. With n equals 4 over the interval of 0 to 2. So in this case, we want to find the area under this curve, going from 0 to 2, using 4 rectangles. Okay? How do we do this? Well, we first need to identify the width of our rectangles, and the width is delta x is equal to b minus a, so 2 minus 0 over 4, and this comes out to 2 over 4, and this comes out to 0.5. So the width of our rectangles is 0.5. And then we need to find our different x sub I. So what are our x sub I? X sub 1, the first sampling point is going to be 0.5. X sub 2 is 1.0. X sub 3 is 1.5. And x sub 4 is 2. So these are the different points at which we'll evaluate the height of our rectangles to determine the area under the curve. And now what we can do is we can use our Riemann Sum Formula. So the sum from I equals 1 to 4 in this case, up to 4 because we're using 4 rectangles, of x, f of x sub I times delta x will simply equal, delta x is always 0.5, so it'll be 0.5 times the function evaluated at 0.5 plus 0.5 times the function evaluated at 1 plus 0.5 times the function evaluated at 1.5 plus 0.5 times the function evaluated at 2. Okay, this is our width. This is the height of the rectangle. These are the 4 rectangles we're using. We're calculating the area of each rectangle and adding them up. Let's actually calculate this. And so if we do this, we get 0.5. We can actually factor out the 0.5. F of 0.5 is 0.5 squared minus 2 times 0.5. So this is our first term, plus f evaluated at 1 is 1 squared minus 2 times 1, okay, plus f evaluated at 1.5 is 1.5 squared minus 2 times 1.5. Finally, plus f evaluated at 2 is 2 squared minus 2 times 2, okay. And to save you guys the arithmetic here, this comes out to 0.5, or you can check the arithmetic, I should say, times minus 0.75 minus 1 minus 0.75 plus 0, and this comes out to minus 1.25. Okay, minus 1.25. So what this means is the area under this curve from 0 to 2 is minus 1.25, approximately. This is an approximation because we've only used 4 rectangles to approximate this curve. Keep in mind what we're doing. If we have some curve, we're going from 0 to 2, we're approximating this curve with 4 rectangles, like this. 4 rectangles, we're adding up the area to get the area into the curve. One final point, how can we get a negative area, negative 1.25? Well, this means that, what this actually means is our curve happens to be below the x-axis, and so our rectangles look like this, and therefore we're getting, since the curve is below the x-axis, the area comes out, and you get negative areas in this case, positive areas if the curve is above the x-axis. Okay, that concludes part 1. Then I'll finish this example problem in part 2.